Welcome to Chem Talk. Ever wish you had, like, the ultimate cheat sheet for something complex?
The simplest possible version.
Exactly. Well, today we're doing a deep dive into chemistry's version of that, empirical formulas.
Ah, yes. We're essentially finding the most basic recipe for a chemical compound.
And we figure it out just from knowing the percentage of each element inside.
That's the idea. It really takes us back to how early chemists started understanding new stuff they found. They do what's called elemental analysis.
Elemental analysis. Sounds important.
It was crucial. It's the process of figuring out exactly what percentage of each element makes up a compound. That was their starting point.
Okay, so you get the percentages. Then what's this empirical formula you get from that?
Right, the empirical formula. Well, it's the chemical formula boiled down to its simplest form. It shows the lowest whole number ratio of elements in the compound.
So like the bare bones ratio?
Precisely. Think about baking. If a recipe needs, say, 2 cups of flour and 4 tablespoons of sugar, the empirical formula kind of here is just 1 part flour to 2 parts sugar.
Yeah.
Same proportion, just simplified down.
Gotcha. The simplest term.
Exactly. And here's something interesting for ionic compounds, like salts that form those big crystal lattices.
Yeah.
Their formulas are always empirical formulas. Their structure means we always write them in that simplest ratio.
Oh, wait, really? So table salt, NaCl, that's it. That's the empirical formula already.
Spot on. Now compare that with molecules. Take ethene, for example. Its molecular formula is C2H4.
Okay, C2H4, 2 carbons, 4 hydrogens.
But that tells you exactly what's in one single molecule of ethene, the true count.
So what's the empirical formula for ethene?
Well, you find the simplest ratio between 2 and 4.
Which is 1 to 2, so CH2.
You got it, CH2. It shows that fundamental 1.2 ratio of carbon to hydrogen atoms.
And those little numbers, the subscripts?
They represent the mole ratio. So CH2 tells us for every 1 mole of carbon atoms, you have 2 moles of hydrogen atoms in that ratio. Okay, that makes sense. Ratio is key. So if we only have the percentages from that elemental analysis, how do we actually, calculate this simplest ratio? Walk us through it.
Sure thing. It's a pretty logical process, actually. Step 1. You just assume you have exactly 100 grams of the compound.
Why 100 grams?
It's a neat trick, because if you have 100 grams, the percentages directly become grams. If it's 70% element X, you just say you have 70 grams of element X.
Ah, clever. Skips the calculation. Okay, 100 grams, percentages become grams. What's next?
Step 2. Convert those grams of each element into moles. This is super important.
Right, moles are like the chemist's dozen, a way to count atoms. How do we do the conversion?
You use the molar mass for each element. You find that on the periodic table, it's the mass in grams of 1 mole of that element. Grams divided by grams per mole gives you moles.
Got it. Grams to moles using molar mass. Step 3.
Step 3, we find the mole ratio. Take the moles you just calculated for every element in the compound.
Yeah.
And divide all of them by whichever mole amount is the smallest. Divide everything by the smallest number. What does that achieve?
It makes one of your elements equal to 1, and it shows you how the moles of the other elements compare relative to that smallest one. Gives you a starting ratio.
Okay, setting a baseline. Then what? Step 4.
Step 4 is the dream scenario. If all the numbers you get after dividing are whole numbers, or really close, like 1.01 or 2.99.
Close enough to round.
Basically, yeah. Within about 0.1 usually.
Yeah.
If they're whole numbers, bingo. Those numbers are the subscripts in your empirical formula. You're done.
Nice. But I suspect it's not always that clean.
You suspect correctly. Sometimes you get numbers that are clearly not whole numbers, like 1.5 or 2.33. That brings us to step 5.
Okay, step 5 for messy numbers. What do we do?
You have to multiply all the ratios you got from step 3 by the smallest whole number that will turn all of them into whole numbers.
Give me an example.
Okay, say you ended up with ratios of 1 for element A and 1.5 for element B.
Right, 1.5 isn't whole.
So what's the smallest whole number you can multiply both 1 and 1.5 by to get whole numbers?
Multiply by 2. 1 times 2 is 2, and 1.5 times 2 is 3. Both whole.
Exactly. So your empirical formula would have subscripts of 2 and 3. A2, B3.
Got it. Multiply everything through until it's all whole numbers.
Okay.
I think I'm ready. Let's try that sample problem you mentioned. Compound of iron and oxygen.
Yep. Analysis shows it's 69.94% iron and 30.06% oxygen.
Oh, okay.
Find the empirical formula.
All right. Step 1. Assume 100 grams. So 69.84 grams of iron, 30.06 grams of oxygen.
Perfect. Step 2, grams to moles. We need molar masses. Iron's about 55.85 grams per mole. Oxygen is about 16.00 grams per mole.
Let's get calculations. 69.94 grams Fe divided by 55.85 grams per mole. Let me see, about 1.879 moles of oxygen.
Great, so we have 1.252 moles in Fe and this 1.879 moles of oxygen.
Great, so we have 1.252 moles Fe and 1.879 moles of oxygen. Now, step 3.
Divide both by the smallest number. The smaller one is 1.252 for iron.
So 1.252 divided by 1.252 is 1 for iron. And 1.879 divided by 1.252. Calculator says about 1.501.
Pretty much 1.5.
Yeah, definitely not a whole number. Okay, so step 4, check for whole numbers, is a no. We go to step 5.
We do. We have ratios of Fe1 to O1.5. What do we multiply by?
Like the example before, we multiply by 2.
And what do we get?
Iron, 1 times 2 is 2. Oxygen, 1.5 times 2 is 3. So Fe2O3.
That's it. The empirical formula is F2O3.
Which is, isn't that just rust? Iron oxide?
It is indeed common rust. See how the process gets us there from just the percentages.
That's actually pretty cool. Okay, thinking about our audience, how does this connect to things like, I don't know, movies or games?
Oh, definitely. Imagine scientists in a movie finding some new alien material, right? Like vibranium in Black Panther or kryptonite or something.
Okay. Assuming they're made of elements we could analyze.
Exactly. If they could figure out the percentage composition, they could use this exact method to find its empirical formula, the simplest ratio of its alien elements.
Huh. The simplest formula for vibranium. I like it. What about games?
Think about crafting systems. You often have basic recipes, right? Maybe a simple health potion needs mystic herb and pure water.
Yeah.
The empirical formula is like that fundamental ratio needed at the, let's say, molecular level for that basic item. 1 herb to 2 waters, perhaps, as the simplest required combo, even if fancier potions add more stuff or have different ratios.
Oh, okay. Like the core requirement. I also thought about pixel art.
How so?
Like the empirical formula is the smallest repeating block of pixels. You know, maybe 1 red pixel next to 2 blue pixels, that little unit, CH2.
Ah, I see. And the whole molecule, C2H4, is like a larger pattern made by repeating or building on that unit.
Yeah, that small repeating pattern is the empirical formula, visually.
That's a great analogy. It really drives home that the empirical formula is just that simplest whole number ratio.
But we have to remember what it doesn't tell us, right?
Absolutely crucial. It doesn't tell you the actual number of atoms in one molecule for molecular compounds.
Like our ethane example, empirical is CH2, but the real molecule is C2H4.
Exactly. The molecular formula gives the true count. The empirical formula just gives the ratio. You'd need more info, usually the molar mass of the whole compound, to figure out the molecular formula from the empirical one.
So knowing the empirical formula is often just the first step in identifying a new substance.
Precisely. It narrows down the possibilities a lot.
Okay, let's quickly recap the steps. 1. Assume undergrams percent becomes grams.
2. Grams to moles using molar mass.
3. Divide all mole amounts by the smallest mole amount.
4. Check if the results are whole numbers. If yes, you're done.
5. If not, multiply all ratios by the smallest integer to make them all whole numbers.
And that gives you the empirical formula, the simplest whole number ratio, a cornerstone concept in chemistry. It's like knowing your basic flour to sugar ratio before you try baking, or your wood to stone ratio for crafting that first tool in a game.
Fundamental stuff. So here's a final thought to chew on. If you discovered some totally unknown substance, you did the elemental analysis, you found its empirical formula, what's your next move? What's the next scientific question you'd ask to really unlock what that substance is and what it could do?
That's where the real fun begins, isn't it?
Yeah.
Lots of possibilities.
Definitely something to think about. And before we wrap up, a special shout out to the amazing geeky gamer science teacher who created this fantastic deep dive into the world of chemistry for us today.
Here, here. Great stuff.